All right, so they released the 2026 AP FRQs, so I'm going to show you guys how to solve the first one here. This one's not too bad. I was actually happy to see this one. So for part A, the first section, it says write the ground state electron configuration of the potassium ion. So when potassium becomes an ion, it loses a single electron. And so originally it has 19 electrons. So then we go to the electron configuration of argon. And then so now we're looking at 18. So then for the potassium ion, its configuration is 1s2, 2s2, 2p6, 3s2, and then 3p6. That 4s1 electron is the one that got ionized and removed. So then this is going to be our configuration for our first question here. You can also do the noble gas configuration, but you can't just put the argon noble gas. You can't just put argon in brackets. That's the cheat code. You guys can't do that. So then you have to pick the noble gas right before it, which would then be neon. And then so you pick up with the 10 electrons from neon. So then it's probably going to be something like this. So for the second part, they then ask, well, which has the larger radius when you're comparing the potassium ion and the potassium atom, and then explain your reason using the principles of atomic structure. So then, like I was just saying, before it becomes an ion, that last occupied sublevel is 4s1. So then that's on the fourth ring compared to now the potassium ion's outermost ring only being on the third energy level. So then that is your justification for the atomic structure. So then we would say that the potassium atom has a larger radius. And then my justification would be because it has one more energy level. In comparison to our ion here, where it's like as soon as it becomes ionized, boom, then you go down to the third energy level. For part B, it gives us our data table, and so someone's doing an enthalpy reaction here, and they're dissolving the potassium chloride in water. You have the given masses for both substances, and then you have the initial temperature of the water, and then the final temperature of the solution once your potassium chloride is completely dissolved. Part B says describe how the student can use the temperature readings during the experiment to determine when the dissolution is complete. So when you dissolve a salt, you kind of just look for the salt to no longer be solid, right? But they want you to use the temperature readings to identify when it is completed. And then so we do have a change in temperature here from the initial and the final values. And so you want to look for that constant temperature. So when temperature becomes constant, that is when your dissolution is most likely finished. Because if the salt is completely ionized now and is being attracted to water through ion dipole, the change in those attracting forces is going to result in the change in kinetic energy of the solution. And then so that becomes constant. That is then your final temperature of the solution. That is when the dissolution is finished. For C, part I, it asks us to calculate the magnitude of the thermal energy, the Q value, in units of joules, that is transferred during the dissolution. So when the salt dissolves, what does that transfer of energy look like? And they want us to show the work that leads to our answer, and then we're assuming that the solution has a heat capacity of 3.95 joules per grams times degrees Celsius. So we're going to use our Q equals MC delta T equation. We're calculating Q of the solution. And then so we need the mass of the solution, which means that we now have to take both of these into account. It can't just be one of the two. So then in our setup here, we have the 97.5 plus the 6.80 multiplied by the given heat capacity, which is here. So then the 3.95. And then we have our change in temperature. And so let me just make some space here. We then have our final temperature minus the initial temperature. And then when we do our calculations here, we end up getting negative 1400.75 joules. And then so that is the transfer of energy in joules when you have your salt completely dissolved based on the given mass value and the given heat capacity of the solution. For double I, it wants us to calculate the value of the molar enthalpy of the solution. So the total change in energy in kilojoules per mole based on the amount of the KCl that dissolved, which is also given, but given in moles, so the 0.0912 moles. And then show your work that leads to your answer. And so we already have the Q value in joules, but we are eventually going to have to convert that to kilojoules. So you can do that initially, or you can do that at the end. So in order to convert joules to kilojoules, we end up dividing by 1,000. So then we have the negative 1400.75 divided by 1,000. And then that converts our number into this lovely 1.40, basically, kilojoules. So then that's going to be the numerator of our expression, because delta H is equal to energy, or Q, divided by moles, which would then be N. And then and this is still negative. Don't forget that it's negative. So we have negative 1.40 kilojoules divided by the mole amount given in the prompt, which is 0.0912 moles. And then we end up getting a number, which then is going to be negative 15.36 kilojoules per mole. Even if you end up converting into kilojoules at the end, before you convert, your number comes out to be negative 15,359 joules per mole. You divide that number by 1,000, boom, you end up getting the same thing. So then this is going to be our answer for, oh, lovely. This is going to be our answer for part II. So then D says the calorimeter is not perfectly insulated, which means that you have some transfer of energy from the surroundings to the inside of the calorimeter. And then they want to know, would this cause the magnitude of the delta H of the solution that we calculated in our part here to be greater than, less than, or equal to the accepted value, and then justify our answer. And so because there's a loss or an addition of energy into the calorimeter, we can't assume that this Q value that we had is 100% accurate. And then so they're saying, hypothetically, how would your actual compare to our experimental one? So my prediction is that it's actually going to be less than. And it's because of this Q value here, right? Like the number of moles is going to be constant. Like the moles is not going to change. But it really comes down to this change in temperature here, which would result in a different Q value that we calculate. And so if it's not perfectly insulated, the delta T would be a little bit different. My guess is that the delta T is not going to change as drastically. So that means that overall, your delta T will be smaller, which will then result in a smaller Q value. And then if we use a smaller Q value, that gives us a smaller delta H. So that is how we came up with the less than. So then that whole justification, so less than, because the delta T would be smaller, due to a loss of energy to the surroundings. Or it would even be something where, because you're decreasing the temperature of the solution, the air in the room is probably warmer than 21.1 degrees Celsius. So that warmer temperature of the air would actually increase this final temperature value. And then so it's not as small as it should be, which still results in a smaller delta T. So I don't know, just be on the safe side. It could be loss or gain of energy here, but definitely going to give you a smaller delta T overall. So here in this scenario, we have equal mass values of our two salts. We have rubidium chloride instead of potassium chloride. However, even though we have equal mass values, their molar masses are not the same, where if you divide by this respective molar mass, this gives you fewer moles in comparison to this having a greater number of moles. So they tell us that the molar enthalpy of these solutions is pretty much the same. So if we want to convert our mole amounts into joules using the molar enthalpy, we'll actually get a smaller amount of energy. If you have smaller moles or fewer moles compared here, we'll get a greater amount of energy because you have greater moles. So then it's not asking about, well, just the change in energy. It specifically wants the magnitude of the delta T. So then it says, well, if you use the rubidium chloride instead, how would its delta T compare to the delta T when you use the potassium chloride? So like we said, fewer moles means that you're going to have a smaller amount of energy. And so if you have a smaller amount of energy, that means your delta T is also going to be smaller. So we would say that the delta T of RBCl is smaller than the delta T of KCl because there are fewer moles of RBCl, which produces or requires less energy. So then if that energy value is different, you're going to have a different delta T as a result. So for part Fi, they give us the KSP of the rubidium salt at 20 degrees Celsius, and they want us to write the net ionic equation. So for I here, we have the unionized salt, which is solid. And then we end up with the rubidium ionizing with a +1 charge because it's group 1. And then chloride ionizing with a -1 charge because it is group 17. And so those would be the respective charges. And then that is our net ionic equation. Even though this is reversible, I'm pretty sure you could just write it as just going in the forward direction. And then you get your separated ions, boom. Because water doesn't really play a role in the net ionic equation here. For double I, it wants us to calculate the molar solubility of the KCl in a saturated solution at the same temperature, and then they want us to show our work. So then we can use the KSP expression, where KSP is equal to the molarity of our ions multiplied by each other. And then they give us the KSP, which is the 57. And then we just plug in our variables for both of these. So because it's a 1-to-1 ratio, we end up with 57 being equal to the molar solubility times the molar solubility. So we get S squared. So to undo the square, we take the square root. So S is then equal to the square root of 57, which is approximately 7.5. So that is our molar solubility. Oh, and then, don't forget your units. 7.5 molar. Triple I then wants us to compare the solubility here to a solution that already has 1 molar of KCl dissolved. So then they're asking, will the molar solubility of rubidium in the 1 molar KCl solution be greater, less than, or equal to the molar solubility that we just calculated here in part double I? And so there is a common ion between these two salts, right? The chloride ion. So if we think about this, we already have 1 molar of the chloride ion present before this even proceeds in the forward direction. That's our common ion, where if a common ion is present, it will inhibit our salt from ionizing and proceeding in the forward direction. So if we think about this as well, this term here, it won't just be S. It'll actually be 1.0 minus S. Or sorry. Or 1.0 plus S, my bad. Yeah, it'd be positive. And then so, this expression now becomes 1 plus S. So then if we rearrange this, we end up getting a smaller number here, which means that if we take the square root of it, this number should then be smaller as a result. So then we would say that the solubility is going to be less than due to the presence of a common ion, which is the chloride ion. This prevents the forward reaction. So the solubility will decrease for the RBCl, for the rubidium chloride.